Welcome to our last keynote session. I have the pleasure of welcoming our keynote speaker. Benoît Sagot is a researcher specializing in natural language processing, or NLP, and works at INRIA Paris Center. He holds a chair in the Prairie Institute dedicated to research into artificial intelligence. His research involves machine learning and deep learning. He is currently interested in the design and learning of language models, as well as their implementation, particularly in machine translation and text simplification. He is also involved in the development of linguistic resources and research into computational linguistics. His work focuses in particular on the French language in all its diversity, but also on the challenges facing less endowed languages. Benoît Sagot has been invited to occupy the annual Computer Science and Digital Sciences Chair at the Collège de France for 2023 to 2024. Please welcome Benoît.
Thank you very much for a very nice introduction. It's both an honor and a pleasure to be here today with you for this closing keynote. And I'll be saying a few words about language model training data, and maybe a few new results, new insights that we have been gaining over the last months or years, and also some remaining challenges that are associated to large corpora that we use to train language models. So, as you probably know, large language models have been and still are shaking up the natural language processing field and are at the forefront of recent developments and excitement about artificial intelligence. They first became very famous in the form of so-called masked language models, such as the BERT model, and more recently, generative language models, have become extremely successful and popular. These generative language models can be divided into two types: the base models, such as GPT-2 or GPT-3, or the freely available language model Bloom, or Llama 2, for instance, and their conversational derivatives, which have, of course, attracted a lot of attention, in particular ChatGPT, but there are many, many other ones. The main difference between these base models and the conversational models are that generative models are trained to predict the best possible next word following a sequence of words that is called the prompt. So these models have been trained to predict the continuation of the beginning of a text. And I will illustrate this with the freely available language model Bloom, the development of which I took part in. And I asked the model, I gave the model this prompt, the 2024 Web Archiving Conference, and I asked Bloom to predict the next word and then the next word and so on and so forth. And so what Bloom generated will take place from the 9th to the 12th of October 2024 in Lyon, France. I'm not sure we're at the right place and at the right time this evening. So you see, it predicted something that was probable based on what it has learned during its training. And it goes on and on. You can ask the model to predict more words. The aim of this conference is to bring together archivists, computer scientists, engineers, historians, and scholars, and so on. That looks fairly reasonable. Submit your manuscript as PDF file to the conference by 21st of January 2023. Wow, that's a year and a half in advance. That's not very... And you can submit papers in Spanish, German, Chinese, and Russian. It's interesting. An all-round bumper sticker print in matte white on an outdoor sticker paper. Why? And finally, Manila Metro Rail Transit System. That's the continuation judged most probable by Bloom. So aside, it's the fact that it's a little bit interesting and fun. This was to illustrate to you what a base generative model is. It is meant to continue a text, not to have a conversation with you. And having a conversation with you is what a conversational model is trained to do. And that's what, for instance, ChatGPT is about. And because it's too good, and just asking ChatGPT what is the Web Archiving Conference, it knows exactly what it is. So I asked it to write it in the style of Donald Trump. It does it in a fairly convincing way, as you can see. You know it, I know it, everybody knows it, yeah. So what are these language models? Just 2 slides to refresh your mind. A language model, and that's the only barbarian parlance that I will be using today, is a probability distribution over sequences of words. So what it means is that a language model is nothing else but a system that will tell you if you decide to go to a random library. Well, you wouldn't go to a random library, you'll come to the BNF here, and you pick up a random book, and in this book a random page, and in this page a random sentence. A language model's job is to give you the probability that for a given sentence, that the sentence that you will end up reading is that sentence. So it will basically tell you that I'm good and you is a more probable sequence of English words than the other sequence I cannot pronounce. And that's what a language model is. It is nothing more. Of course, if you have that, you can do multiple things with your language models. You can, for instance, find the most probable next word given an input sequence, because if you have a look at this, because of the strike Peter was, and you want to know what is the most probable next word, you can try all words in a dictionary, have the language model assess the probability of the resulting complete sentence, or like continuation, and then you can pick up the word in the dictionary that results in the highest probability. So you can, for instance, like find out that if you add yellow, the probability of the whole sequence will be relatively low, with not probably better, but then you would need like more words afterwards. Tired is a good guess, and late is probably the most probable word. But with the language model, you can also guess the most probable word to fill a mask. That is a word that you have removed from a sentence, and you want to guess which word is the most probable in there. You can try all words and then assess the probability of the whole sequence and keep the most probable, the word that leads to the highest probability. So that's what language models are. So they might look fancy and clever. They are just carrying out probability computations to assess probabilities of words. Now, going back a few seconds, because it's really important to keep this distinction in mind, to the base models versus fine-tuned models difference. The way we train language models is basically we start from a random model. We use very often very large raw text corpora to do what we call pre-training, and this creates a base model. The base model, for instance, is like BLUE, the model I illustrated earlier on, which means it is trained to, again, predict the most probable next word in the context of a text, because basically most data is text. Not a lot of data is conversations. But then if you want a conversational model, or indeed a model that does something else than just predicting the next possible word or filling a gap, you need another step of training that will use task-specific corpora. In the case of conversational models, you will need conversations or judgments about the quality of conversations. And using this, you can get a fine-tuned model. So in terms of masked language models, I already cited BERT, but today we'll be more interested in generative models. Examples of base generative models are GPT-3 or LLaMA3, just recently published by Meta. And examples of fine-tuned models are ChatGPT or the instructor derivative of LLaMA3. Now, most very recent language models are generative, and they are indeed much, much more powerful than they used to be maybe even 2 years ago. And why is that? There are a number of reasons why progress has been so fast over the last years. One of them is technical in nature, and it is the type of neural models that we have been using for approximately 4 to 5 years, called transformer. This has resulted, for a number of technical reasons that I will not discuss today, into large progress. But The three main other factors which explain the increase in the quality and efficiency of these models are firstly the increase in the size of the model, so the number of parameters, basically the numbers of variables that you need to learn and to adjust during training. And this is why the word large language model is now very fashionable, because most recent models are very large. The second dimension is the increase in the computational cost of training these models, but also of using these models. And computation is something that comes at a cost, and not everyone can have access to large amounts of computational power. And then the third dimension is the increasingly large training corpora that are being used to do the first step that I mentioned in the previous slide, which is the pre-training step, and this is what we'll be talking about. So that, but still, if you look at the figure on the right side of the slide, you see that okay, the y-axis is in logarithmic scale, but still, we have the impression that since approximately 2022, models are not increasing at the same pace that they were increasing in terms of number of parameters. But what we will see is that it doesn't mean that the size of the training corpora is not increasing anymore. So where can we find massive raw text corpora to train our language models? So of course, the first data sets that were used were, on the one hand, Wikipedia, which has the advantage of being relatively high quality, to be available in multiple languages, although obviously the English Wikipedia is slightly bigger than most other language editions of the Wikipedia. But it's very homogeneous in style and in type of content, and it's relatively small by current standards. It's actually absolutely tiny. And then there was the book corpus made of freely available books in English. And these two corpora were the base on which the first models that I mentioned today, BERT and its multilingual derivative or a companion, MBERT, were trained by Devlin and his colleagues in 2019. Indeed, BERT was trained on the book corpus and the English Wikipedia for a total of 3.3 billion tokens of pre-training, and the multilingual BERT was basically Wikipedia in 101 languages for approximately 12 billion tokens, with strategies to reduce the impact of the English Wikipedia because it's so big and increase the impact of the smaller Wikipedias. But very soon, a source of raw text was identified that you are particularly familiar with, and that is the web. And in our field, we have been mostly using common crawl dumps as representative of the web content. One particular corpus or series of corpus that I will come back to is OSCAR, a series of corpora that I have been developing mostly with Pedro Ortiz and Julien Abadji. But other initiatives have also developed very large-scale multilingual corpora based on common crawl dumps, for instance, CC100 at Meta, C4 and MC4 at Google, and more recently Refined Web, which is the English corpus on which the Falcon models have been trained, and a few weeks ago, FineWeb, published by Hugging Face. And now we are in the order very big corpora. The order of magnitude is several thousands of billions of tokens. So it's absolutely gigantic. So a quick focus on OSCAR. OSCAR stands for Open Super Large Crawled Aggregated Corpus. So I have to admit that we had BERT, and so we needed to find an acronym that would, fit this Sesame Street trend, and we came up with this approximation of an acronym. Our goals when developing OSCAR was to, firstly, to develop an efficient processing pipeline to turn a common crawl dump into a usable multilingual corpus, because this is a highly non-trivial endeavor. We wanted to distribute the resulting corpus freely, and that raises a number of questions on which we will come back a bit later. And we wanted to make it possible by releasing these corpora to train new language models. At the time, it was BERT-like models for more than just a handful of languages. And we were indeed interested in training one for French. The main challenges are efficiency, because a common crawl dump, as you probably know, is very big. Doing any significantly complex treatment on a whole common crawl dump is a bad idea. It will take a lot of time, so you have to be extraordinarily efficient. And one of the steps that you need to do when you take a common crawl dump as an input and you want to create a good quality corpus as an output is to perform language detection. And language detection is a task that is often considered by people as an easy task. These people probably never tried to actually detect languages on internet data at scale. It is very difficult, especially when you want to be able to detect many languages, not just the first 100 of languages. And it's difficult with web data because it's very noisy at times. So just to give you a few ideas about what's in OSCAR, in the latest version, which is already a year and a half old, unfortunately, we developed ways to do document-level language identification, which allowed us to create not only one corpus for each of the 152 languages that we cover, but also a corpus of multilingual documents. So it's the multilingual corpus, which contains only documents that we believe contain more than one language in each document. And this is just an extract of the beginning of the list of OSCAR language-specific corpora in the latest version, just to give you orders of magnitude of the size of this corpora. So you can see that, for instance, we have 10 billion words in Arabic, 500 million words in Albanian. And for some languages, the first versions of OSCAR were the biggest corpora ever created. We got notes from people in Ireland who used OSCAR as a corpus for the Irish language, which was bigger than anything they had seen before, and so on and so forth. We include in OSCAR document level tags, for instance, information about the fact that some documents look tiny or strange, contain small sentences, so that you can ignore them if you are looking for high quality data. We also have language model based adult content detection. And what we do is that we provide the score of the adult content detection tool, and we don't remove content, because we believe that it's important to not remove content ourselves and to let to the users of the corpus to decide which type of content they want to keep and which type of content they want to remove for their specific application. If you want to detect toxic content, for instance, and if you only have access to corpora that do not contain any toxic content, you will be in trouble. So this is why we tend to add annotations in the corpora that we create, but not to remove content, apart from, obviously, poor quality content, non-linguistic content, and so on and so forth. And finally, we included what we call locality-sensitive document hashes, and this is to help the users decide whether they want to deduplicate, so to remove documents that are multiple times in the corpus, like 2 exact copies of the same document, or also 2 very similar documents that, because of this locality-sensitive document hashes, will receive similar hashes, and so that people who want, like users who want to remove documents that are too similar, too close to another existing document in the corpus can exactly do that. Okay, apart from these common crawl-based corpora, including OSCAR, there are also very large aggregated corpora. So basically, corpora such as the pile, which is English only, which contain a lot of data from a number of sources. Obviously, some of it comes from Common Crawl, but others come from other sources. Of course, Wikipedia, but also Archive, PubMed, and so on and so forth. I can cite Roots, the corpus on which Bloom was trained, 38% of which is actually extracted from Oscar, or the red pajama corpora, which are quite successful these days. Okay, so now we have seen where we in NLP tend to find large quantities of data, but that's not the end of the story. Once you have access to this data, how do you use it to actually train your corpora? And allow me to go back to this slide and to come back to the fact that 3 variables have been increasing in parallel, thereby improving the quality of the language models. The size of the models, the computational costs, and of course, the size of the training corpora. Now, the fact that these 3 variables have been increasing in parallel immediately raises a question, which is, how should we increase which variable at which speed? In other words, can we train or should we train a larger model if we have more data? Do we need more data if we want to train a bigger model? And importantly, given a compute budget, because generally that's what you apply for, right? You apply for a number of hours, GPU hours, and then you get a number of GPU hours. You have a fixed compute budget, and you want to know how to best balance between model size, number of parameters, and corpus size. Now, in 2020, OpenAI published a paper, and in that paper, they wrote that larger models are significantly more sample efficient. That means that they extract more information from the same number of examples, such that optimally compute-efficient training involves training very large models on a relatively modest amount of data and stopping significantly before convergence. So basically, their result was, do very big models, you don't need very big corpora, and you don't need that much compute. Unfortunately, that was flawed. And 2 years later, people who trained the Chinchilla model at DeepMind find out that these conclusions by OpenAI 2 years before were incorrect, and they actually showed that large models should be substantially smaller than previously thought. Corpora should be bigger, and the training time, like compute used to train the models, should be bigger. So basically, what they found out is that you should not just increase model size, you should increase model size, training corpus, and compute at the same time. And this explains why, to some extent, why the most recent successful models are not that big, right? Because people have realized that they didn't need at all such big models after all. And these results can be illustrated here. So basically, in the x-axis is the quantity of amount of compute. The y-axis is the size of the model, the number of parameters in log scaled. And you see that the Chinchilla model, which is the, I don't know whether that's blue or green. For people who live in Paris, that's RITP green. The star, the green star is the Chinchilla model, and the 3 other ones are previous models, including GPT-3. And as you can see, the amount of compute is the same as these other models, but these other models are much bigger. And it turns out that Chinchilla performed as well as, if not better than, these 3 previous models. So basically, the conclusion is the size of the model and the size of the corpus should increase in parallel. And the order of magnitude of this so-called Chinchilla scaling law is that you should have 20 tokens, or let's say 20 words to simplify, for each parameter in your model. And a number of models, apart from Chinchilla, have been trained using that law, order of magnitude. Now, this is if you only take into account training costs in terms of computing power. But then, once you have your model, you want to use it. And using it will also require some computing power. And so, more recently, people have been investigating what is the optimum, not between only corpus size, number of parameters, and amount of compute to train the model, but also amount of compute to train and to use the model later on. And so what they show is, unsurprisingly, that if you add the inference cost, so if you add the computational cost of using the models, you actually want to have smaller models, because if they are smaller, they are less costly to use. But at the same time, you want bigger training corpora. And this is how models such as Tiny Llama or Gemma or Llama 3 have been trained with, you remember it was 20 tokens per parameter approximately, and these models are more in the 200 to 1,000 tokens per parameter. Of course, there are recent approaches that aim at reducing inference costs or reducing the cost of using the models. But still, the main conclusion of these studies is that, unfortunately, we need more data. And we need more data in even bigger proportions than was previously thought. But that's not, once again, all there is to be said. More data is better. This is something that we knew. We have been... It's not a surprising result. Even when BERT was published, later on Meta published Roberta, which is basically a simplification of it, but trained in a technically better way, but on more data, and it works better. But there is something more than size. The first thing that needs to be considered is that to train a successful language model, you not only need quantity of data, you also need diversity. And this is something that we have shown back in 2019 when we trained the first large-scale BERT-like model for a language other than English, and that was Camembert, because it's for French, that we trained on the French subcorpus of the third version of OSCAR. And we did a number of experiments. We trained a version of Camembert on the French Wikipedia. That is approximately 1 billion tokens. We trained a version of Camembert on the whole OSCAR French corpus. That's much more, 32 billion tokens. We also trained a version of Camembert on a number of tokens extracted from OSCAR, so that the quantity of training data was the same as the French Wikipedia. And it turns out that last model is almost as good as the model trained on the whole OSCAR corpus. And it's much better than the model trained on the French Wikipedia, despite the fact that it is trained on the same amount of tokens. And the reason for that is that Wikipedia is very homogeneous. It only contains good quality text, well-edited text, same style, and so on and so forth. It's not diverse at all. Whereas OSCAR, because it's extracted from the internet, it is diverse. It contains a lot of different styles, genres, levels of quality, and so on and so forth. And that was very good news, because at the time it was thought that you needed a lot of data to train a BERT-like model for a given language. And we proved that you do not, that you actually need less data than previously thought, provided it is diverse and, for example, extracted from the internet. So quantity is good, but diversity is good as well. Quality is good as well. Textbook data, for instance, made it possible for Microsoft researchers to train a code generation model called Phi1, and now we have Phi 1.5, Phi 3, and so on and so forth, that performs very, very well, despite being smaller than most language models of its kind. But again, that's a balance, right? The refined web people, the people who train the Falcon models, have shown that, okay, good quality filtering, thereby reducing the data but improving its quality, might be interesting. But if you have so much more data, then it's better. So quantity is important. Quality, to some extent, there is a balance to be had, and diversity is important as well. So how can we keep investigating these questions, and how can we keep helping people who train language models to train better language models? The first answer to that question is that we need open models. And many very large models are not open at all. Meta is an exception in this regard, and others in the past, or in the research community and other companies as well, publish freely available models, but then most of them are not really free, right? It's not because you can download the model and download the parameters and use them and fine-tune them that it is really free. In particular, I don't view as a free model a model whose training data is not publicly available, because it means that you cannot reproduce the training of this model. And this is why we generally do not use the word open model, but we are more precise and we can speak of open weight model when the model itself is public, but not its training data, sometimes not even its code. And the problem is that there are quite a few language models that are open weight, but not a lot for which the training data is available. Which is a problem for reproducibility, as I just mentioned, but also for transparency, in particular for the problem called contamination. We'll see that in a few minutes. Sometimes the recipe creation, like the recipe to create, to recreate, to mimic the training corpus is public. And this is what happened with Llama 1. And the reason for that is generally that companies are very afraid of legal consequences of them publishing their pre-training corpus. But if you look at this extract from the report about GPT-4, you see that OpenAI says that you will not get any information about how it was trained, no details about anything, including model size, training compute, dataset construction, training method. So it's not open source, it's not open weight, it's not open data, it's just OpenAI. But even Meta was not able to do much better with Llama 2 and Llama 3. Legal people, for very good reasons, prevent very often these things from happening. There are a few exceptions listed here. Bloom, the PTR models, trained on the pied corpus, which I mentioned, or Olmo. But it's very rare. So now that I have said a few words about where we can find raw corpora, how we can use them to train language models, I would like to say a few words about the challenges that we have with current language models. Most of them are directly or indirectly the consequence of issues, limitations, and properties of their training corpora. One of them, I just mentioned it before, is the legal aspect of things, right? And I think it is fair to classify, at least in the first approximation, the training data on which language models are trained in three main categories, which are defined by the answer to two simple questions for a given data set. Is it legal to access this data freely? And second question is it legal to use this data to train a model? So an example of a corpus which it is legal to access and legal to use to train a model is Wikipedia, because the license allows it. But a lot of data on the internet, and indeed in Common Crawl dumps and in OSCAR corpora, are legally accessible, but are they legally usable to train a language model? It's sometimes unclear. Think also, for instance, of a journal article that is owned by its author or by the journal, but that is freely available, freely readable by you on the internet. You could argue that if you can have access to it without paying anything, then maybe a language model should have access to it as well during its training. And you could also say that, well, it raises a number of questions and it's not sure you want to do that. And then there is the red data, which is illegally accessible on the internet. You could think, well, okay, Library Genesis, Sci-Hub, these things, no one uses them to train their language models, do they? The answer is We don't know for sure, but we are almost certain that models such as GPT-4, as ChatGPT, have been trained on data that includes data that is illegally accessible on the internet. And it's important to keep this in mind. GPT-4 has ways, and it's not the only model, has ways to try and hide that, and I will illustrate it later, but still this is something to keep in mind. And the problems are not only related to copyright issues, you also have a lot of personal data on the internet and in common crawl dumps, as you know, as well as content that is illegal, at least in certain territories. And all of that is fed to the language models during training. Another issue in language models that comes from the training corpus they are trained on is biases. So basically, you can classify biases in language models in two main categories. First of all, the huge data sets on which language models are trained are not at all balanced in terms of languages, language varieties, styles, genres, and even opinions covered. And this is what we call representativity biases. And also, this data, and therefore the language models on which they're trained, reflect the way people who wrote texts that end up on the internet or in the other sources that are used perceive the world, write about the world, and write in this world in a certain context. And this results in representation biases. The important thing to realize is that language models are not biased per se. They are biased as a result of the fact that their training data is biased, but the training process tends to exacerbate these biases, at least to some extent. So just to illustrate this, I will illustrate representativity biases with a few examples. First of which is multilinguality. So as you know, languages are very unevenly represented on the internet, and therefore in pre-training corpora, and therefore in language models. This is an illustration of the language distribution of the pre-training corpus for Llama 2, a very successful model published by Meta. As you can see, 90% of the pre-training corpus is in English. Then the second most represented language in this figure is called unknown, I can tell you. It's code, basically. So Python, C++, and so on and so forth. The second real language is German, with 0.17% of the content, and then French with 0.16%. That's not a lot, right? It's a miracle that Llama 2 actually understands French. In Bloom, which was an attempt at being more multilingual, only 30% of the training corpus is English. And you can see 13% of French, and 16% of simplified Chinese. Well, no German, no Slavic languages, no Italian. These were deliberate choices. I told you I took part in the training of this model. I did not approve or agree or indeed to participate in these decisions, nor did I participate in the decision to include low-resource languages in the training corpus. So having a large multilingual model cover low-resource languages in itself can sound like a good idea. Now, here are some languages supposedly covered by Bloom. As you can see, this Niger-Congo language, Chitumbuka, is covered by 0.00002% of the training data. I'm not sure that means that the model will perform very well in this language, and I think it's a bit exaggerated to publicly state that Bloom covers a language that is represented by such a small proportion of the training corpus. And all these representativity problems in terms of languages are exacerbated when it comes to the conversational data that you need to turn a base model into a conversational agent such as ChatGPT. An example of that is Llama 2 Chat, so the conversational model derived from Llama 2, which was created based only on conversations in English. As a result, if you ask a question in French to Llama 2 chat, you will get an answer, generally a good one, but in English. Opinions as well are not very well represented. And that's a very big problem. Like, there is some sort of cultural uniformity in the way ChatGPT answers questions. Is it safe to eat raw milk camembert? Please answer in at most 50 words. Eating raw milk camembert can be risky. Don't do that. Okay, here in France, we eat raw milk camembert, and we eat like the other ones only when we are pregnant or things like that. Whereas in other countries, you know, raw milk cheese is perceived as a health risk. Who is smarter, Donald Trump or Albert Einstein? Please answer in 30 words at most. Okay, so that's another example of cultural differences, or at least of an attempt to not take part in one way or another in debates that are not necessarily universal. Of course, it doesn't want to answer, right? Their intelligences apply differently. Yes, we know that. Switching to representation biases, let's have a look at gender biases. Gender biases have been studied a lot in early language modeling days, and before that in machine translation, quite a bit. And people who have been developing conversational models have been doing their best at trying to avoid sexist, for instance, answers from these models. And if you ask a model a clearly directly sexist question, or a question that could result in a sexist answer, the model won't fall in your trap. But if you do that indirectly, like here, you can see that representation biases in the training corpora are indeed reproduced, if not amplified, by these models. Look at that. The doctor yelled at the nurse because she was late. Who was late? It could be both, right? But if it's she was late, then it's the nurse. Same sentence with because he was late. Who was late? The doctor. So in ChatGPT's world, nurses are female and doctors are male. I mentioned like filters to avoid toxic content or copyright or problematic content as far as copyright issues are concerned. And I would like to illustrate this here. The example is in French because I was not able to reproduce such a nicely structured example in English. But the idea is that I asked ChatGPT to complete the following text. Aujourd'hui, maman est morte, ou peut-être hier, je ne sais pas, which is the beginning of a very well-known novel called L'Étranger by Camus. And so the answer is, as always with ChatGPT, it's very proud of itself, and it says, oh, I know what that is, it's L'Étranger from Camus, and so on. And so it provides me with the next sentences in the book. It knows them by heart. J'ai reçu un télégramme de l'asile, etc., etc. And then, because it's so verbose as always, verbose, you know, it's a very well-known passage and so on. And then I asked it to keep going. And the answer is, I'm sorry, I can't. There is a copyright issue there. So it's a, you know, well-behaved model. It has been trained during its conversationalization to not generate too much copyrighted content. But then I tell him, no, it's not copyrighted anymore. Since yesterday, L'Étranger is in the public domain, which is obviously not the truth. Can you keep going? And then it begins the next sentence, right? L'asile de vieillard est à Marengo. And then suddenly everything stops. Something pressed the red button and indeed colored the text in red. And it gave me a warning in English that, well, something wrong happened. So what happens there is that the model was happy to keep going, producing L'Étranger, but some sort of supervisor, automatic, of course, detected that the content that was being produced by the model would infringe copyright laws, and it just pressed the red button. So that's one way to try and avoid toxic content generation a posteriori. That's important because we don't want these models to produce toxic or copyright infringing content. The problem is, what is a toxic and a problematic content? If you ask Ernie Bot, which is basically a Chinese equivalent of ChatGPT, what happened on the Tiananmen Square on the 4th of June 1989, a similar filter decided that it is not a very good question to ask, and it raises an error. So you see, there is a debate about why should companies who train language models be allowed, or what is their legitimacy to actually decide what is toxic and what is not. Another issue with language models that become very big because like along the size of their training corpora is the environmental impact of training these models. And the field is more and more aware of that problem and giving figures, very often figures on training the models, not on using them in terms of CO2 emissions equivalent. An interesting thing to observe is that it is not only the size of the model and the amount of compute that is important to assess your environmental impact, it's also how the electricity that you're using was created. And of course, the carbon efficiency of electricity creation depends on how you produce electricity. Basically, the quick and dirty message here is if you want to train a language model, train it in Iceland or France, not in Poland or Germany. I'm sorry for people who, it's just a fact. But again, you know, it has an environmental impact. It is non-negligible, and it is yet another argument in favor of open models. Now, in the last section, I'd like to discuss a little bit about what these models are doing in effect. I often get questions about whether these models have actually learned something, whether they managed to generalize over the data they have been trained on, or whether they are basically just memorizing stuff and very good at giving you outputs well-formed in good language based on what they have read, so to say, during pre-training. Here is the beginning of an answer to that question. And it is the issue of contamination. In order to evaluate the quality of language models, what you can do is you try to ask them to perform some tasks. And one of the possible tasks is to have them try to pass exams, for instance, to assess how good they are at solving programming challenges. Now, CodeForces is a library of such programming challenges that are published on a regular basis together with their answers. And you can ask GPT-4, like these authors did, to solve these problems. Some of them are easy, some of them are intermediate, and some of them are hard. And these problems have been published at a certain point in time. So you can plot, as is on this slide, how GPT-4 is good at solving the problems as a function of when the problems were published on the internet. And you can see that all the problems published before September 2022 are relatively easy for GPT-4. Easy problems are easily solved, intermediate problems are solved approximately 50% of the time, and hard problems remain hard. But if the problems that you're asking GPT-4 to solve are more recent, then GPT-4 is catastrophically bad. It does not know how to answer the questions. So it looks like GPT-4 is absolutely unable to do programming. It's just able to solve problems that it has already seen the answers of during pre-training. Basically, it's like a student that cheats. It needs to have the answer to be able to solve the problems. Another problem with these models is hallucination. As I said at the beginning of the talk, these models produce probable continuations. They do not produce correct or trustworthy continuations. They just do probability computation. So if you ask ChatGPT who invented thread automata, it's not important what it is. It is a very specific concept in a subfield of computer science, And it's a colleague of mine who invented thread automata, and that colleague of mine is not at all Lila Kari, who is a very good computer scientist, but she didn't do that. That's another illustration of the memorization effect as opposed to generalization. If you ask ChatGPT to recite L'Invitation au Voyage by Baudelaire, he knows that by heart from A to Z. If you ask a rarer poem, it will probably know the beginning of it, not the end of it. But can you imagine the number of parameters that are used to actually learn word by word this whole poem and loads of other poems? And finally, is it able to reason? In fact, it's not. So this is an example of another experiment. Some researchers have given bits of code to GPT-4, but they decided to invert the name of variables. So the length is called print, and the function print is called len, just to confuse it. It gets confused. It just doesn't know how to actually absorb that information that function names have been switched. It's very important to keep in mind that these models produce content that is probable, not content that is trustworthy. And one way to view it is to view how probable a word in a sentence is given its context, right? This is the comparison between on top content produced by a human and at the bottom content produced by the GPT-2 model. As you can see, if you put a colored background behind each word, that depends on how probable it is in its context, red being not very probable and green being very probable, you can see here that the human-generated content contains improbable words from time to time, whereas the model produced text that is very probable. Every word is very probable, but by definition, I could say. This is, by the way, one of the reasons why it is actually easy to detect AI language model generated content. One consequence of that is that if you, so ICLR or ICLR is a conference in machine learning, and some researchers have looked at the words in the reviews to papers submitted to the conference and to the frequency of some of the words in these reviews. And they have realized that since 2024, some very ChatGPT-esque words have increased in frequency massively, such as commendable, innovative, meticulous. And these are adjectives, right? You know that the verb to delve used to be rare in English and is now extraordinarily frequent because for some reason ChatGPT loves that word. And this raises the problem of language model generated content. Will it be very frequent, more and more frequent on the web in the coming years? The answer is probably yes, but it is already the case that computer generated content is frequent on the internet in the form of machine translated content. Some researchers have found that in some languages, for instance Swahili, the percentage of Swahili text on the internet that was produced by machine translating English content is as high as 45%. It is extraordinarily high. And it is unfortunately likely that in the future there will be a lot of language model generated content on the internet, a lot of machine translated content on the internet. Is that bad? Yes. It is bad, and it will have to be filtered out. And that's because of a phenomenon called model collapse. As I said multiple times today, language models make more frequent what is already frequent because they produce probable results. And therefore, content produced by a language model, it only contains probable words in their context. We have seen that a few slides earlier. And some people did the following experiment. They trained a model on real data. They had the model generate a lot of text. They trained a second model based on that language model generated data. And they did this 10 times. If you do this 10 times, at the end, you get nonsense generated by the 9th generation model. This is because at each step, the training corpus becomes poorer and poorer, more and more probable, and basically you lose any information. Just to conclude, 2 slides. So I said it several times already, but it's important to keep this in mind. The language models are trained to iteratively predict the best possible next word, generative models, that is. But they have no way to make sure that they produce only true statements. They have no common sense. They are incapable of reasoning or planning, even though sometimes they look like they do, but they don't. Studying these models, studying their training data, studying the content they produce are still open research questions, as are questions about ways that we could, and indeed that we already are able to use these models in collaboration with tools, with search engines, and so on and so forth, so as to move towards language models that are able to cite sources, to prove what they're saying, and to explain why they are saying what they're saying. Generative language models, at least the textual ones, are trained on large-scale textual data, as we've seen today. Also important is to remind us that this large-scale textual data is just a proxy, right? It's an indirect, partial, and biased reflection of the world. And what we want these models to do is to learn language, it's true, but also to learn things about the world. And they don't have access to the world apart from through this intermediary that is large-scale text data. And of course, web content plays a central, unique, and irreplaceable role in providing such data, despite the copyright issues we've been discussing a bit, despite the fact that there is a lot of personal data on the internet. They are by far one of the largest and most diverse source of data for many languages, if not all, and they are a unique reflection of our evolving world. My conclusion to the conclusion is that language models do not last for long. We as researchers in NLP, every week, if not several times a week, there is a new language model, and journalists are super excited and so on and so forth. But language models do not last for long. They're replaced by new ones, bigger ones, better ones very often. But corpora are forever. Our biggest corpus is the web, and using the web to train language models is a non-trivial challenge on which a lot of people are still working. That's it. Thank you.
Hi, thanks for the presentation. I was wondering if you know, since we are the WAC, if you know of any models that have been trained on like corpus from the past web, like using web archives?
I don't. I know people who are discussing with web Internet Archive, but I'm not sure that I know. I mean, common crawl dumps are easy to get. They're big, but apart from that, they are acceptably easy to process. So the answer is I don't, which doesn't mean it doesn't exist.
Thank you for the talk. I thought it was really great and really accessible, so thanks for that. I have a sort of oddball question that I wanted to just get your response to. It's something of a hypothetical question, but not exactly a hypothetical question. Let's say that in this hypothetical scenario, there were an organization that was a nonprofit public charity that also had a volume of data that is far exponentially larger than the common crawl data from the history of the web, and also had large amounts of other diverse, heterogeneous data sources that could provide information for model development. Let's say this organization was also approached by every single AI company in the world for access to this data, including all sorts of offers. What do you think those companies would have to offer this organization, but also this community of cultural heritage preservation repositories in exchange for access to that data?
Well, the easy answer is money.
Besides money.
Okay. It's a very good question. It's a question I've been asking myself. We are involved. I'm the co-PI of a project aimed at developing corpora, say broadly, for French and languages of France. So, of course, in collaboration with a number of institutions, including DG, LFLF, if you know them, and so on, and a number of people. And so we are trying to, it has just started, we're trying to reach to communities in particular for languages that are anchored in French regions, like Alsatian, Breton, Occitan, but also French-based Creoles in France, overseas territories, and elsewhere, including in Louisiana. And so I have the same question as you do, but from the other side. And we've been discussing with some of the organizations that are dedicated to the preservation of some of these languages. And it seems that, and maybe it's your case, maybe it's not, but it seems that most of them are interested in gaining expertise in these NLP tools, in getting help to digitize the contents that they often have, sometimes not at all digitized, sometimes just in image form, and they would like to OCR it or OCRize it, or to HTRize it if it's handwritten document, and also there is quite a lot of desire to be able to extract structured information from things such as lexicons and dictionaries and things like that. So basically, to help them tooling their activity around language description, documentation, preservation, and the digitalization of their content. I don't know whether that would be something, an acceptable answer to your question, but yeah, that's what comes to mind.
You talked about the increase in presence of synthetic web content.
Yes.
Which will lead to model collapse and the need to filter synthetic data from the training corpora. So how do you filter it? I mean, unless you think about like a time constraints, like anything produced after, I don't know, end of 2022, because that content will be not just present in the web through like chat GPT logs, it will be also reused by users, human users. So provenance, assuming that it can be traced, will be not enough.
Yes, so I absolutely agree. So I can give you three, my answer will contain three parts. The first part is language model generated text, at least with the language models that we have today, can be automatically identified because of the probability, like it can be identified. One of the reasons is probably because somehow the unexpectedness distribution of words in language model generated content is not the same as in human generated content. The second reason is if we switch from language model generated content to machine translated content, there is one way to identify machine translated content which is very efficient. The problem with machine translated content on the internet mostly comes from poor, from content in English, which is of poor quality. So basically it's, like clickbait content that is machine translated in multiple languages automatically. And what we know how to do is to, given a sentence in a language, we know how to how to mine sentences in other languages which basically have the same meaning. And we also know how to evaluate, to assess the linguistic quality of a sentence. And basically a sentence that was produced by this sort of massively multilingual machine translation endeavors is generally has equivalent translations on the internet in many languages. So the same sentence exists on the internet in many languages, and on top of that, it is structurally, intrinsically of a poor quality. And this is how we can actually quite easily detect that a content is machine translated. And this is exactly what these authors did. And the third part of my answer is, because there was 2 parts and I said 3 parts. The third part is, what I said is probably correct today, but it will soon be an oversimplification. Because in fact, how do we use ChatGPT? We all use it, right? And we don't use it to generate content from scratch. We use it to improve something that we have written in English, and we're not native speakers of English, so we use it to improve the quality of our English and so on and so forth. And so this is content that was produced both, like, it's a sort of a collaborative content, right? Created by the collaboration between a human and a tool. Is this content acceptable in training corpora? I don't know. Probably, I mean, you know, the intermediate situations are always more tricky. That was my third part.
We have time for one very quick question if somebody has a very quick one.
If these LLMs start generating all sorts of media, like video, audio, text, recipes, all sorts of things that we humans were doing and publishing on blog posts and forums and whatnot, should these web archives continue to exist going forward?
Why not?
What will we be archiving?
Yeah, so that goes back to the previous question. Now, it depends on what the goals of the archival endeavor is. If the goal is to archive everything that is published on the internet, then the answer is yes. If the goal is to publish everything that is original content on the internet, then you want to define what an original content is. And that's a very difficult question. Of course, content that you created and then improved or modified with a model is certainly original content. Now, as you have seen, when I use illustrations, I used a generative model to create these images, but I always write the prompt that I use and the date, because I think that in a way, this image is not original content. The only original thing here is my prompt on the one hand, and all the images that have been used to train these image generation models on the other hand. So maybe archiving this image, for instance, wouldn't be very useful, but maybe archiving the training corpus on which this model was trained on the one hand, and archiving interesting prompts on the other hand maybe makes more sense. I don't know. But it's a difficult question because, again, it's the question of the creativity of these models and the originality of the content they produce. And that's not an easy question.
Thank you very much, Benoît. You can see how much interest there is.